Good morning. Welcome to our current episode of Wednesday webinars. This is our last part of our air valve series. In May, you learned about the types of air valves and how they work. Last month, we talked about selection, locations, and sizes for air valves. We also went over an example using the APSLIDE slide rule. Today, we'll expand on that by learning how to use our web-based APSLIDE program. Using the slide rule is a faster method for one or two locations, but it can be very tedious to locate, select, and size air valves for an entire pipeline that could have dozens of stations. Also, our APSLIDE program provides a comprehensive report that shows not only the data that was provided, but the results of the calculations and what valves are suggested. The APSLIDE program has the ability to import and export data. Importing is useful when the customer provides the pipeline data in a spreadsheet. It saves the time and effort to type information for every station individually. Exporting allows the results to be transferred to another user or application so they can import it for their own use. Copying an APSLIDE project lets you save more than one version, allowing for modifications without deleting the original. Also, the way APSLIDE integrates with our other web tools is impressive, and you'll find it to be time-saving and very useful. So there's nothing new or surprising about this list of required information. Type of media determines which type of valves you choose from, clean or dirty air valves. Various units of measure can be used, both imperial and metric, and even a mix of each. From the last seminar, we learned that sizing for air exhaust depends on the filling flow rate. We also learned that vacuum protection depends on the size and pipe and its slope. The size, type, and class of pipe also affect vacuum protection sizing. We know that to size air release valves, flow rate and pressure is required. We often get pressure at the start of the pipeline, such as pump pressure, and apply the same pressure to the entire pipeline. While frequently done, it isn't ideal because the pressure does not remain constant over the length of a pipeline. Using hydraulic grade line is better if it's available. So we'll spend a minute talking about hydraulic grade line, or some people call it HGL. It can be expressed in feet or meters of head. It represents pressure available in the pipeline. In this picture, hydraulic grade line represents actual pressure at each point along the pipeline. You'll notice that it decays along the way and will be at its lowest at the end of the pipeline, and of course at its highest at the beginning. Pressure at the beginning must be high enough so it will still be greater than the elevation at the highest point along the pipeline. If it isn't, there won't be enough pressure to push the liquid over the hill, so to speak, so flow could stop. This blue line represents the pressure APSLIDE will use if HGL isn't provided. In that case, the customer will just provide a pressure at the beginning of the pipe, and we use the same pressure throughout the pipeline. It doesn't look like it would affect our calculations much, but if we take a closer look at example of station number 14, which is the highest point, let's see what it does to us. So I just zoomed in on that view. The difference between elevation and one of the lines, I mean either constant pressure or the hydraulic grade line, the difference between one of those lines and elevation is what's called the working pressure, and that's used to determine the size of the air release valve. That pressure is important. Now looking at this picture, the working pressure based on constant pressure line is 50% greater or so than the working pressure based on the hydraulic grade line. That much air could cause ARVs to be undersized, which means you won't be getting rid of all the air, and you might be, I'll say, decreasing the efficiency of the pipeline. Also, it should be known that the closer to the end of the pipeline, the greater the amount of air will be, because the hydraulic grade line is always decaying throughout the distance, whereas the constant pressure is just that. So the air becomes greater the further down line you get. Now, the next thing we'll talk about is you know, how do you get the information from the customer? And it could be a number of ways. If you're fortunate enough to be able to get the piping profile because the plans and specs have them, that's ideal. And in this particular view, that's what they've got. So you can see there's kind of a split screen. The top half shows kind of a aerial view, plan view or whatever, and the other one shows the pipeline profile for the side. And just some things to point out as you look at this. The top view is handy, but it doesn't really help with everything. But the yellow line, I've highlighted it just to show where the pipeline actually is located. Now, the bottom view is a graphical representation of the pipe. Along the bottom, and I've circled it in blue, is the distance. We call it stations sometimes. And the distance is, in this case, measured in feet. But and there's grid marks that show you all the different steps along the way. But one thing to bear in mind, if you're not that familiar with civil plans, you'll notice, and if you can see it on the very left bottom, the first station point is called 54 plus 40. Okay, what does that mean? 54 plus 40 means, let's see if I can zoom in. 54 plus 40 means actually 5,440 feet. So the surveyors and whatever else, they just like to talk in terms of hundreds of feet. So they say 5,400 feet, but then they add the plus 40 for the individual count of feet. So you'll see that sometimes it just means 5,440 feet. Okay. So, and then on the left-hand side is elevation. Now, in this case, it shows elevation in terms of from sea level. It could be elevation, you know, from any reference point. It doesn't really matter. It could be elevation starts at 0 and goes to, you know, some number up or down from there. But in this case, they said elevation started at 860 feet above sea level. And actually, honestly, the pipeline started at about 895-ish feet above sea level, if you look on the left end of the pipe. And you can see that it slopes downhill throughout the distance of the pipe. There's also some low points and high points. And those points are what matter to us. So the first thing we would do is look at this and record the high points. And yes, probably a pencil and paper is the right way to do it. But look at 5440, or just to the left of it, probably 5420. And at that point, 5420, your elevation is 895 feet. So you move on to the next point. I've shown them with the green arrows. It's either going to be at the next high point or at least a change in pipe slope. So you can see that I've noted first there's something maybe across the road there, so it went down and then back up. That's sort of in the middle. Here, I'll zoom back in on that again. It's easier this way. So you can see that it went down, over, up. So you got two high points, and there's also a low point. We'll talk about that in a minute. And then as you go further over, you can see there's another road crossing, and there's two more high points, and of course, a low point between it. There's also a change in slope, which is what the last arrow represents. So you pay attention to those things. You record the locations. For example, the change in slope here is at 5920. And if I'm just looking across at the top of the pipe, you could use the bottom of the pipe, doesn't matter, but it's about 892 feet of elevation at the location station of 5920. So that's the high points. And of course, we also care about the low points because that's how you calculate the elevation slopes, the changes. So once again, we show low points. And so after you've recorded all these points, the highs and the lows, now you have the data to put it into the program. Or if you would rather, you can grab your little manual slide rule and do each one individually. I think I'd rather use the program. Now, sometimes you get information like this, you have to record your own data. Sometimes you get information that the customer's already recorded for you. on a spreadsheet. And what's interesting about this is they did give us location. The start of the pipe was not at 0, it was at 39,399 meters. And it was also at elevation of 294 meters. And then they gave us the HDL. They gave us everything right here. And that's beautiful. So I'll show you later how this data can be imported right into the program without having to retype everything in, although you can if you'd like. It also gave things that you might want to record, such as tag numbers. Sometimes it's just nice to put the tag numbers at least at the locations where the valves are, and that's for convenience for the customer. Now, another way that we get it, and this is real, this is only about 2 weeks ago I got this one. Yes, it was somebody sketched it on a piece of paper and took a photo of it and sent it to me as a text. But it has the information we need. You can see that at the bottom it shows the gallons per minute. They didn't tell me the pipe information, so I had to gather that from the but it gave me the high points and the stations, distances, low points, and I had quite a bit to go on here. And so as I looked at it, okay, so the green arrows show the high points. I recorded those. On the furthest left green one there, you can see the elevation is 906 feet. And you can also see that the station distance is 2183. That's what I need. I have the same information for the other points. Now, also likewise, I have the low points, which help with my calculations. And I have the distances, I have the elevation. So I more or less have what I need. And I was really happy about getting this until I realized I have to rethink something or else I'm going to have a mistake. And the clue is on the paper here, on the screen. And it's about water flow direction. There, normally we think, and the program thinks, that flow goes from 0, or the lowest number to the highest number. Well, in this case, they show the flow starting at 8560 and ending up at 0, so it went backwards. So I had to do one calculation, which was to reverse the station distances. Nothing else changed, but I had to, if I was going to start with flow in one direction, I had to start at 0 and calculate what the distance is to the next station and so on. So pay attention to flow direction. The program does care about that. Okay. So that was some information about how to gather information, and we're going to spend the greater part of the presentation really looking at the program. And so before I actually launched the program, I thought I would just explain this screen. And when you go to the rep-only website, there's a logo. It looks like the APSLIDE logo on the right-hand side of this page. You click on it, and this screen is the first thing you see. And it's kind of the disclaimer, the lawyer's message. Basically, it's saying we're using common calculations to give you typical results. It doesn't replace using common sense, and that there might be other concerns that affect the results of this. And then you have to say, I agree, before you can go forward. So once you get to that screen, now you're ready to go to the APSLIDE. So let me, one moment, transfer over to that screen. Here we go. And it is mid-morning, so you might as well have your cookies. So accept the cookies at the bottom. Hopefully you have a cup of coffee to go with it. Anyway, so this is the main website, and of course, we currently have a full APSLIDE version on the rep-only website. There is a future plan. It's not in play right now, so we don't know when it'll come, but there's an idea that we want to have kind of a mini version of the website on the public site, or of the APSLIDE on the public site. It'll be similar in function of doing, like what the slide rule does. Because we want the customer to come to you for the real heavy lifting to look at this. But if they want to do a quick sizing, someday we'll look at that. Okay, go to your represented login page, and of course, log in. And now you're on this screen. This looks very familiar. You can see a lot of our tools are across the top of the screen. APSLIDE is the very first one. Click on it. You'll get the disclaimer screen that we already mentioned, and I agree. And now we get to the browser. And it just take a few minutes to explain this. I'll start by saying this browser looks very similar to our other web tools, Configurator and some of those other tools. So I won't go into all the details. I'll mention, of course, a few things. One of them is, you can choose which organization you're in, and of course that's me. But what rep organization you're in, and you can even choose your username. So you could pick down here and have the program you run assigned to you, so you can open it later. You can sort things like project names. You can click on the arrow, and you can sort if there's engineers. I'm not always putting engineering names in, but sometimes I do. You can sort by engineers, project location, and so forth. You also have the ability to search by keywords. I could type in the word example, and I would only get these first 5 here. I wouldn't get everything else, first 6. And you can sort by date ranges or whatever else. So you got plenty of things you can do for searching and sorting. I'll mention some options for any one of these. You can manage means you're opening it. Manage means you're going to go to that program and either print some results or change things or manipulate it in some way. Delete is just what it says. You click on delete, and it's going to make you type the word delete just to make sure you didn't click it by accident. And then copy project. And I like that because when you copy a project, you can have more than one version of it, just in case, look at Decatur force main right here. You can see that I have 2 versions of it because I just wanted to do some what ifs, okay? And then some other things that you should be aware of, definitions. What I cover here today, this definitions page is going to show you a lot of it. It's a handy reference. If you use this program, print it off and hang it on your bulletin board beside your desk or something. Some good info, layman's terms, not real technical. If you want to go more technical, get AWWA M51, and you can read that. Once you go back, I'm going to go back. Also, the instruction manual, very useful, also very similar to what I'm going to be covering today here. It's a PDF document, and it's 15 pages long, and you can see there's various topics by the table of contents, a lot of visuals and so forth. So definitely use the help guide, instruction manual. So now let's go ahead and take a look at creating a project. We're just going to kind of step through a project, just kind of go through each field, not spend too much detail, but still mention them. So on the left-hand side, we're going to talk about project reference. Let's go ahead and type one in. Let's just say, Sartell Water Plant, or Sartell Aqueduct, like we have one. But anyway, Sartell, Minnesota, and maybe an engineer. And so that's data that you need. It's optional data, but it's good information next time you open it. Then you have to decide what's my media is. Is it water or is it wastewater? When you choose that, it determines which group of valves you're picking from, water or wastewater valves. Design flow rate. Now, this is where you take data that's given to you from the customer. And, you'd ideally like to kind of know their normal flow rate. Maybe you look at their max flow rates too, but their normal flow rate, whatever it is. And in this example, I'm going to use 15,000, one more zero, and I'm going to click gallons per minute as units. Flow rate, and I'll explain what that means. We require that flow rate is filled in, but actually it's more of a convenience for us. What it does later on is it shows you how fast the pipeline is filling at 1,200 gallons per minute. You want to try to be below that 1 foot per second of filling rate. And so you pick a number that will get you there. It won't stop the program or crash it or give you wrong results, but it's a reference for you. Generally, I'll use a number that's smaller than the design flow rate. I happen to know that 1,200 works, but I usually pick something small. I might have picked 1,000 or something, and then you can change it later. Linear units, is it metric or is it English? We're using English. And for this example, we're just going to use pipeline pressure. That's the pressure at the beginning of the pipe. We're not going to use hydraulic grade lines, and we're going to use 75 pounds per square inch. Could have been bar or kilopascals. Now we get to the next part. We have to describe the pipeline. We have to tell the program, how long it is and how high it goes and so forth. So we're going to just start with the first field that's optional, but you can put in a description. So I put in pump station. You can put in a tag number if you want, but for this one, there's no valve there, so we probably don't need a tag number. So station, we're calling it 0. And for elevation, we're calling it 0. I'll show you how changing it affects it later. And then now you can click from cell to cell to cell. I can add the next piece of data in by clicking here, which is what I'll do, and then I'll explain in a little more detail something that's easier. But we're going to make our station 750 feet, and our elevation is 20 feet. And by now, some of you might recognize it's the same example that's on the slide rule. And I happen to know that that's a high point, and this is an optional piece of information, but it's useful to me. So why not put it in there, high point? So I mentioned I was clicking from cell to cell to cell. You can save time by just hitting your tab key. Every time I tab, it moves you, let's just say I was here, and I can tab to the next cell, I can tab to the next cell, and look at what happens when I tab again. It creates a new row for me. So it automatically creates as many rows as you need just by tabbing from one to the next. I think it's very handy. So we know it's 1,000 feet, and the elevation is 10. And this is the end of the pipeline. And to be perfectly honest, when I'm in a real hurry, I don't type in all this data. I'll come back and add it later. But I'm just showing you what you can do. And I also am going to put a air valve AV number 1 for a tag number, optional information. Now, we have to tell it what kind of pipe, because at this point, it only knows the length and the elevations. It doesn't know anything about the pipe. We provided a nice tool, and it says right here, autofill with predefined pipe data. So if you click on it, and you do need to, you have to tell it what kind of pipe it is. And you also have to tell it what length, what span of distance is the pipe is this pipe going to be? Well, it starts at the beginning, so it starts at node 0. So you leave that at 0. We're going to use stainless steel pipe or steel pipe. We're going to go 24 inches, and we're going to go schedule 40, just like the example on the slide rule. And we're going to hit select. What's going to happen is the data that comes up is going to show you that it starts at node 1. It shows you that you chose a 24-inch pipe, and here's the type, and here's the class. And then from our own database internal to the program, it knows, okay, this type of pipe has an outside diameter of 24 inches, but has a wall thickness of 0.69 inches. So then from that, it knows what the inside diameter is, actual inside diameter. That helps during the calculations. It also gives you some information about the pipe. And I guess before I really explain this too much, M51 tells you that you should never exceed 5 PSI as the difference between the pressure on the outside of the pipe and the pressure on the inside of the pipe. So if you're at an atmospheric pressure of 14.7, you don't want to be less than 9.7 PSI on the inside of the pipe. You need to size the air valve that prevents it from getting below the 5 PSI differential. Except for, they also say if it's plastic pipe, don't do 5, do 3. Plastic pipe's more fragile, so it uses 3 psi. And so if I would have chosen PVC, that number would have said 3 instead of 5. It also, AWOL recommends a safety factor 4. So even if it just calculated the strength of the pipe, which is a ratio of the diameter and the wall thickness and some other stuff thrown in there, it still says put a safety factor 4 on there. Now, why does that matter? Well, if I know that if I have a ductile iron pipe that's 6 inches in diameter, I could pull a full vacuum on that and you still can't collapse a pipe. It's okay. It's not going to damage the pipe. It might damage gaskets or other equipment in the pipeline, but it's not going to damage the pipe. But what if instead I had a 72-inch diameter pipe with thin wall steel? That pipe is pretty vulnerable to collapsing. It doesn't have a whole lot of strength. It's got good hoop strength for internal pressure, but not when the pressure is greater on the outside. So this program calculates, if I used a big pipe, let's just pick one. If I used a big pipe, let's go 96-inch pipe, standard, select. Oops, I can't have 5 psi before it collapses. It'll collapse with only a 1 psi pressure differential. That's a big deal, and that's why we asked the question about pipe type. One of the reasons why. Let me change this back to the correct pipe here. So I'm going to go back to stainless steel and go to 24-inch. Oops, I do that a lot. 24-inch and class with schedule 40. And you notice the data changed back to 5 psi. So it says use the lesser of 5 psi or the actual calculated pressure based on pipe size. The other thing you're going to see is it gives you something called the Chesney coefficient, and you don't have to memorize that. But if you can click on, anytime you can click on these little symbols, and you can get a description. It's a measure of pipe roughness determined by the type of pipe. The Chesney value for ductile iron is 110. The Chesney value for steel is 130 and 190 for plastic pipes. Okay, so I like to say the higher the number, the smoother the pipe. If you can think about it like that, this makes sense. So it uses that in calculations for the air vac sizing. So right now, this is the pipe information. I gave you a lot of information about that. You could have more than one type of pipe throughout the span of the pipe, and I'll show you that example later. So I've given it all of my starting data. I've given it my pipe profile. I've given it my pipe information. So let's calculate. Anytime you make a change, you have to hit the calculate button. And here's what you get. You get a graphical representation of the pipe starting at 0, moving 750 feet, and the slope raises to 20 and moves further and the slope lowers. And it shows you the elevations and it shows you the length on the left and the right sides. It also shows you a representation of the pressure, you know, either hydraulic grade line or fixed pressure. In this case, we use 75 psi as a fixed pressure. So it shows you that there's a lot of pressure in that pipe. And you've got a lot of differential between the pressure line and the elevation of the pipe. There's a lot of good working pressure there to use, okay? You can always get that. Now, here's the result after you hit calculate. You get, you know, similar to what the slide rule would have given you, a 6-inch air vac valve, body style 1800 with a 1/4 inch air release on it as well. So it's a dual body air vac valve. And this is usually enough. I could save this, I could print the document, I could send it to my customer, and it's usually enough. But sometimes people want to know more. So they're going to, let's see here, they're going to say, click more information. And when you click more information, all the same data you had before is there, but there's other information. It shows you the working pressure at the valve location, 66 psi. It shows you the calculated slope coming to the pipe, shows you the calculated slope going away from the pipe. The air vac valve sizing is based on the greater of the two, the greater of the absolute value of either one of those. which is the 0.04 in this case. So it figured out the air vac valve has to be 6-inch. And what it also tells you, though, air vac, of course, is inflow. The vacuum protection is inflow. So it says, hey, there's about 57 cubic feet per second of inflow. And translate that to what size orifice would that be? Well, that's 5.349 inches diameter orifice. Well, we don't have a valve that size, but we have a 6-inch, so we default to the first valve bigger. Likewise, outflow orifice, you know, remember when we were filling the pipeline, air going out, this is the size orifice you would need for outflow. And as we've said before, usually inflow or vacuum protection is the more critical piece of information, and outflow is smaller than the inflow. So we just use the 6 and we're covered for inflow and outflow. Also, it shows you what size air release valve is required based on the pressure, the working pressure, and the flow rate. And 0.239 PSI, well, we don't have an orifice that size, but you round up to the nearest orifice and it's a 1/4 inch orifice. So anybody who wants more information, you could give them that. As a matter of fact, it always shows when we do the printout. Now the other thing, when I had less information, it defaulted to the lowest cost valve that does the job. However, there's oftentimes more than one type of valve that can do the job. Maybe this customer said, hey, you know, cost is fine, but I really want stainless steel. So I could pick that one instead. And you know, once I go back to less information, it still shows ASU. And you could go ahead and when you print your quote, I'm sorry, when you print your report to them, it'll show that. Okay. One more thing I forgot to mention, I will, is we already said that the pipe is stainless steel. It's on the rougher end of the spectrum, and you get a 6-inch valve as a result. Well, I guess I'll ask you guys to tell me, what do you think is going to happen if I would choose a PVC 24-inch valve? And I'm just going to pick a DR21, which is typical. And every time you make a change, you have to calculate. So if the first thing you're going to think is, well, okay, it's smoother pipe. You know, it seems like it's more efficient. Probably, if anything, I'll use a smaller air valve. That's exactly opposite. It forced you to go to an 8-inch air valve. The reason is, if you broke the pipeline and water started flowing out of the pipe, because the pipe is smoother, water will flow faster. So you need an air valve there that can let air in faster, because water is going to rush out faster. So kind of an interesting little trivia, if nothing else. Let's go to another example. We're done with this one. Let's go to another example. I'm going to browse products. I already have the example made. You can save it if you want. I don't need to. I'm going to just leave it without saving. But it is nice that it reminds you that maybe you should. Example 4 is the one I'm going to do now. I'm going to manage this. So I've got data that's preloaded. Before I go through the data, this is what the pipeline looks like. So you have an overview before we start talking about it. Now let's look at the data. I'll do it quickly. We were given wastewater as our example, 6,000 gallons per minute. 1,000 gallons per minute of filling flow rate is what we chose. And this time we were given the hydraulic grade line. They gave us the pressures at each station. And so I typed it in. You'll notice that station started, in this case, at 0, and it went all the way up to 6750. And one point that you should know, you will get an error if for some reason you type something wrong. So if for some reason I went from 0 to 3,000 to 2,200, it won't work. It'll tell you, say, hey, something's wrong. And the error shows up at the top. It says node station 3 must be further than the previous station. So go back down here and fix it to 3,200, and you're good. Okay. And if I, chose to add another location, I could hit a plus sign and I could type something in, and I could add some more values here. I won't do it, but if you wanted to or you forgot one. So I'm going to hit X, and that deletes this row. Okay. Now, we've got the elevations go up and down, along the length of the pipe, but hydraulic grade line elevations will always start at the highest at the beginning and always end at the lowest at the bottom, okay? Because energy is consumed throughout the length of the pipe. So the hydraulic grade line is always decaying, if you will. Now I also have pipe, I'm going to calculate so you can see the screen, both screens. I also have two types of pipe. So starting at node 0, which is here at the beginning, node 0, it says station 0, node 0, and elevation is at 700. So hovering your mouse gives you some good information. I chose the pipe, but the customer said, hey, at 5,000 feet, I have an elevation of 698, and I'm also changing my pipe to ductile iron. So I can go in there and add more locations. Now, what we did for convenience is we put the background of the chart graph changes so that you have a visual indication that the pipe has changed. So if we added more pipe, it would be gray again. It just alternates gray, white, gray, white. So that is the information that went in. And, I wanted to mention this is the hydraulic grade line. This was given to us. And so what's interesting is if you look at some of these, like this high point, if I would have used the hydraulic grade line at the 800, or the given pressure at the 800, I would have been almost twice as much pressure at this air valve than I would have been if I used this pressure. So it greatly can affect sizing, especially towards the end of the pipe. Let's look at results. And I guess I've shown you most of this. This particular one, it was sewage air valves, and we chose sewage, and it gave us some different results. ASV, which is a sewage air vac valve, ASU, because it was cheaper than the combination ASV, and so forth. If I wanted to, if I had water instead, let's just change that to water. Nothing else changes, let's just change that to water. Water, there. Have to hit recalculate. And now the valve selections changed to AVVs, clean water, air vac valves. And a couple of them have the air release function on them as a dual body design. Okay, I'm going to say now, maybe the customer, like I showed you before, maybe the customer only wants AASUs, they want stainless steel, maybe they're next to an ocean that's corrosive air, whatever, or they just know that ASUs work better, they can still pick them and do that, okay? Now let's go ahead and print the report. We've created this, let's print the report. You can enter this data, this should be a familiar screen to you. You can enter data, you can even save it as default, and we hit print. You don't have to enter that data, by the way, but it's nice on a report to be able to show. So the report has been saved to your download folder, and what you can see from the report, it looks a lot like what you just saw on the screen. The given data, some of your contact information, the given pipeline data and hydraulic grade lines, the given pipe information, the chart, and I forgot to mention that there's symbols that represent air valves, so at a glance you know that a full circle filled in is an air vac valve, a circle half and half is an air combination valve, and a circle with no fill in is just an air release. And then, of course, there's a lawyer statement, because we want to make sure everybody understands that we give you good results, but based on common calculations. And here's your report that you can give your customers. So it does give you, the calculated air release orifice. I'll zoom in a little bit. It gives you the calculated air release orifice. It gives you the inflow orifice required, 2.7, so a 3-inch valve was used. It does tell you what the outflow would be for filling, and as usual, it's usually going to be smaller than the inflow, so it's normally not going to be your gating item. But it gives you good information that a customer can use. Okay, we're going to move to example number 5 and look at something else. So I'm not going to save or anything, but I'm going to browse APSLIDE projects, and I'm going to go to example number 5, manage. And manage means I'm opening up and looking at it. What we're going to see is wow, that's quite a pipeline. about 8 miles long, and it's up in the mountains and goes over and up and down and over a lot of stuff. So the data we'll look at real quick, and the reason this one's unique is that we're given flow rates in gallons per minute. We're given linear units in meters. We're given, and hydraulic grade line, of course, is also given to us in meters because it's technically it's a linear unit. It's an elevation. So we've got mixed units here. Now the data is here. I will tell you that a few slides ago I showed you a spreadsheet that was given to us by the customer. Fortunately, we didn't have to type all this in. The customer gave us that data and we were able to put it in here. This information, so it was nice. We could just jump right into entering or putting it in there. And then we had to manually enter the pipe data. So we do know that at the start of the pipe, it's ductile iron all the way for the gray area. And then when we get to 10,440 meters downstream, they changed it to PVC C900 pipe. Now, we do have to tell it when the pipe starts, and even though these are distances in feet, each one of these points is a node. Every time we enter a location, it's a node. Okay, node 5, node 6, node 7, node 8. So this is at node 20. And to show you what I mean, back up here, it's at node 20. It's right here. So, oops, I guess I can't highlight it. But anyway, it's at node 20. So it helps you to tie it back to the input data that you gave. You'll notice that because ductile iron is rigid, pressure of 5 is allowed for the delta P between the external pressure and the internal pressure. But the second part is plastic, and you're only allowed 3. So that changes the sizing parameter. Also, the Chesney coefficient, you went from rough pipe to smooth pipe. That also changes the sizing parameter. But the program considers all that. You don't have to worry about it. It's all taken into consideration once you put this data in here. So you're going to see sometimes that you get, oh, I wanted to, before I do that, I want to show you node 21. Node 21 is important because of a few things. The hydraulic grade line and the elevation is very close to each other, so the working pressure is very small. That affects air release valve sizing, and the slopes are pretty high, so that affects air vac sizing, and since it's plastic pipe, it affects it again. So we can take a look at this slope, and then I'm going to explain that it, you know, what's important about it. But there's a feature in here. I'll just show you now. It's the right time to show you. This is 8 miles of pipeline. There's a whole lot of information there, and it's almost a little hard to digest. You can hover your mouse over each point and get some of that information. But what if you wanted to see just this area? So I'm going to show you a trick. You can click anywhere and drag. Click and drag, and whatever you've selected now is zoomed in. So now that's your zoomed in view. You're not looking at the whole pipeline, you're just looking at this section of the pipeline. And further to that, you can pan around. If I hit the pan, I can slide, you know, left or right. The scale of the chart automatically adjusts based on where I panned. Click again to stop panning. And I can even reset to go back to normal. But I brought up about node 21, so let's take a look at it in a zoomed view. So once again, pretty steep slopes. You're going to have a big air vac valve, very low working pressure. So you're going to have a very large air release valve there. And we make it. That's fine. But you have to, it might require special consideration. So when we get down to node 21 here, it's going to say contact DeZURIK for the correct valve. Don't panic. We have one. Don't. It just means that our database of typical valves won't cover this one. It's going to be a combination of a, I'll tell you what it's going to be. It's going to be a AVV 12-inch 1800 body with a 200 air release valve. And so that's, why do I know it's a 200? Well, because if I do more information, I click that quickly, I see that it requires a 0.506 air release orifice. Well, a 200A doesn't have an orifice that big, and a 200, well, and I got caught up in APCO terminology. It's a 200 series, so technically to go to an orifice that big, you would need a model 207. It's the 200 series air release valve with a 1-inch orifice. Or I could round down to 0.5 and probably be just fine. If I did a 0.5 size orifice, it would probably be a model 205. I'm guessing, but anyway, contact DeZURIK for those. Don't panic. That's my point there. All right, let's go to another example, and I just want to show you that we can do big pipelines. And honestly, this isn't the biggest one. This just happens to be the example I have loaded in here. And well, actually, before I leave, I should tell you that if I hit calculate, where is it? Pardon me while I scroll. I'm going to get finger cramps in a minute. Anyway, if I hit calculate, it still happens pretty fast. That was fast. I do know that if you have something much bigger than this, there might be a wait time, but that's pretty fast. So anyway, browse APSLIDE projects. We're going to look at example number 3. I'm going to leave. I'm not going to save changes. Let's go back to my example 3 because I want to show you the export, import, and so on real quickly. I want to mention to you that there's 2 types of export. Export project is for sending the data that you see on your screen to a comma-separated file that somebody else can import by using import project. It's just data. It's everything you see on the top of the screen, everything you see, on these screens right here. Whereas there's another, and I'll show you that, but there's another function called export results. Export results, I'm going to click it and show you. It does also export information in a comma-separated value type thing you can open in Excel. And the results shows you all the stuff that you see at the bottom of the page. Node number, station elevations, pipe type, but it shows you results here. So if you want to export this to your own program, or if you want to, I guess, present it in a different way, this results is there for you for that purpose. But let's go back to what I was showing you before, export project. If I want to export this project as is, you can export it by clicking right here. It creates a comma-separated value document. Click on it. It's going to look a little bit like what you saw before, but if you look a little closer, it's different because this shows you the input data that you put at the top of the program. It shows you the station distances, elevations, hydraulic grade lines, pipe stuff, and all of the data that the program would need to run a calculation. Okay, it's not the results. Giving this to a customer wouldn't be very meaningful, but it's the data. So if I wanted to send this information to, Jack Harold, for example, he could open it on his own name and import it. So I'll show you how. So let's just say I'm creating a new project, and I'm going to import the project. So choose the file, the one I just sent out there. I'm going to choose it. It has a funny name, but you can give it any name you want when you export it, after you've exported it. So look what happens. I'm going to click on import. And other than the header or the beginner information, you'll have to type it in again. It gives you everything. It shows you the flows, the units, all the pipeline data, all the pipe information. They ran the calculation, all the same outputs. So if you want to transfer your calculations to someone else, if you want to send it to me or your application engineer, maybe you've made a try and it's not quite what you wanted, you export the project, email it to us, and we'll import it and look at it. That'll work just fine. Now, I showed you at the very beginning there was this 8-mile-long pipeline and the customer gave us a spreadsheet. There's another thing you can do, which is download the import template. This is a blank template. It looks just like what I just showed you, but if I had the data, I don't have it handy, but if I had the data, I could just paste the HDL data there, I could paste the station data there, and the other information there, and then when I go back to the program, all I have to do is enter what kind of pipe it is, and by the way, I can also enter my flow rates and flow types and so forth. So the only thing I don't have is the pipe information. It's easier to enter that in the program. So if you have a download import template and somebody gives you a spreadsheet, you can paste their data into our template, and then you go back to import and do what I just showed you a minute ago, which was bring it back in, like so. Okay. All right. Well, I think we're really using up all our time, and I'm kind of at the end of what I want to show you on the program. So let's go back to the just a couple more topics, very brief, on the PowerPoint. Okay. So kind of in closing, some things. You know, first of all, tips for success. You know, you got to use it to learn it, but some things that you might come across right away. Sometimes we get asked by our customers, why is our air vac valve suggestions bigger than some of the competitors? Well, we use the very conservative AWWA M51 calculations. And one of the things it does is it considers a sizing for vacuum protection based on a complete total pipe break. Not real common as a total pipe break. It's usually because somebody knocked a hole in the pipe or there was a corrosion blowout or something else, which is a partial break. So sometimes our competition assumes a partial pipe break, so it results in smaller air vac valves. Just to let you know, we can do those same calculations. Once the customer agrees what the basis should be based on a full pipe break or partial pipe break, and they understand that it's less conservative, then we'll do it. Let us know, you know, send it into DeZURIK and we can do it and help you out. Another thing is some of the information customers give us might show every single elevation change, even if they're minute. But our program determines that every elevation change is a new node, and it might put an air valve there. So, you know, I talk about tweaking the pipeline. If there's some of those minor elevations, I'll delete that node because I don't want to have all that noise in my calculations. My practical approach, and nobody wrote a textbook about this, it's just my practical approach, is that I would remove minor changes where the elevation only changes a little bit, maybe less than half the pipe diameter, or even less than that. Anything with bigger elevation changes than that might require an air valve, so leave it in there. Another thing that you should be aware of is this is meant for pipe runs that slope no greater than 45 degrees, or if you calculate the slope, that's 1.0. That's beyond the range of APSLIDE. You'll still get an answer, but it may not be, you know, exactly accurate. And also, when you're sizing valves for vertical runs, like in vertical turbine pumps and so forth, come to us for those. Don't use the APSLIDE program. But for any of these reasons, you know, we can help. Give us the data. That's really the message here. Now, we have some resources that are always available. Of course, the APSLIDE slide rule, they're free, request them anytime you want. APSLIDE air valve sizing tool, which is what we just talked about, so I'll stop talking about that. We have bulletins that help you with choosing the right valves, valve selection guides, which help you with that. Also, on both websites, public and rep, depends on what you're looking for, we have media types. One, DeZURIK valves and pump station applications is a good information. It's a video that's very, very good information. We talked about last week. ASU combination air valves, for example, is another video. But what about specifications, drawings, and training videos? So there's all kinds of good stuff out there. If you have a question, we're always there to answer it, but you might find a lot of your questions are answered when you go out to our website. And so that kind of concludes, this was a very brief overview of the APSLIDE program. I hope we gave you some useful information so you can use it and help your customer. And of course, as I said, if you prefer, we can help you with the program. Just gather the required information and contact your application engineer or your regional sales manager. But I need to say, if there's any advice I can give you, is open up the program and try it out yourself. It's the only way to really learn it. You roll up your sleeves and play with the program. You won't break it, and you might discover that it's easier than you think.